Welcome. In this lecture, I'm going to talk about temperature calculations in the wellbore. So let's consider a segment of tubing of length delta L, and we have some fluid coming into that tubing, and we have some fluid leaving that tubing. So one could be flow from the reservoir, and two could be flowing towards the wellhead. And that tubing has a temperature, let's say average temperature, T fluid TF, and it will exchange heat with the formation, with the environment. Okay, in this case, is the formation that is surrounding the tubing. And that heat can be in two ways. So if the temperature of the fluid is higher than the temperature of the formation, so then you have some cool down. You have that the heat is going from the fluid to the formation. You're having losing energy to the formation. Or it can be the other way if the temperature of the fluid is lower than the temperature of the formation. Then the heat flux will go from the formation to the tubing, and then the fluid is getting heat up. Okay, to represent that situation, we're going to use a Q, this line, this arrow, and then we're going to use Q dot. And we have some conventional signs that we're going to use for our conservation equations that we're going to talk about just now. The Q entering the system, if I have the fluid is being heated up, that I consider to be positive, and if the fluid is getting cooled down, that is considered to be negative. Simply that's arbitrary sign convention. And so to calculate temperature, we are going to make a control volume on this segment of tubing, and we're going to apply some energy conservation equation, or the first law of thermodynamics for open systems. So that is what is shown down here in this text, is that all the terms that I have exchanging energy across the boundary. So is the Q, that we all know this is going to be some number because we are getting cooled down or heat up by the formation. We have some work, and typically we don't have any shaft work like in a pump or a compressor or a turbine, that we have some work flowing out and into the volume, but we have some work that is done by the fluid by getting itself in, pushing in, and getting it pushed out. So that's some sort of a piston work that I express with PV, and I should include there because I have that work there. And then I have the energy that comes in minus the energy that comes out, and that term is I can express in terms actually of specific energy, which is the mass flow times the specific energy, and that term has three components, which is the internal energy, the potential energy, and the kinetic energy. If you see that equation tells you, let's say that we have that the Q is positive, that means that the fluid is getting heated up by the formation. So that will mean that the energy out is higher than the energy in. That makes sense because the temperature of the fluid is increasing, and then this U probably is higher here than here. Okay? If it's the opposite, the fluid is getting cooled down, the Q is negative, then that means that the energy 1 is bigger than the energy 2. Okay, so that's what this equation is representing. So then with Q, we neglect that the W, we neglect that W, and the PV, we merge that together with the U, and then we end up with a specific enthalpy, H, which is another thermodynamic property. So PV and U, all of them are thermodynamic properties, and then simply when I combine them together, I end up with another thermodynamic property, H. And that's how it looks like, H, specific enthalpy, potential energy, and kinetic energy. Then I can express those in terms of deltas, difference between in and out, and I can also express it in differential term. Looks like that. So for most cases of flow in tubing of hydrocarbons in tubing, I can say that this term, the variation in kinetic energy, is relatively small and is compared to the rest. Okay, so we can simply neglect that term. That is not the case, for example, if we have a low pressure gas, then in that case it will be important. Or if we have some changes in the cross section, like for example we have an obstruction in the tubing, which is we have a very small opening, or if we have flow in a choke, then in that case we cannot do that. Yeah, but for flow in a tubing, that usually I can do that approximation. So now let's go and look more in detail about enthalpy, how enthalpy looks like, because that will be important to say how do we solve that equation, because we have to solve that equation along the tubing, and then we will be able to find temperature. But what is not so clear from here is that temperature is not explicitly expressed in any of these terms. Okay, so we have to know where temperature is involved here. Okay, so specific enthalpy, H, is simply another BO property, just like viscosity, density, etc., that depends on P and T, and I can calculate at a given P and T with an EOS, equation of state, and a composition, for example. By the way, the H that we are considering in that equation is the H of the mixture and is the mass fraction of gas times the enthalpy of gas plus the mass fraction of oil times the enthalpy of oil plus the mass fraction of water times the enthalpy of water if we had any water. And this X, for example, of gas is the mass flow of gas divided by the mass flow total. Again, that value will change depending where you are in the tubing or at which pressure and temperature. If I'm undersaturated, then I will be fully percent either gas or oil. And then when I'm saturated, then I will have some percentage of the fluid that is going to be gas and that is going to be oil. Okay, so this is the mass fraction. Here you see an example of the enthalpy table. You see that a given pressure and temperature, you have two oil and gas. That means that you're in the saturated region, 300 and 148, you have two. Okay. But then comes a point at which, for this low temperature, then I only have oil. I don't have any more gas. Okay. But it's like that. The units of enthalpy, kilojoule per kilogram. And let's see how it looks like with the pressure and temperature. So this is if the fluid is an oil and I have at a fixed temperature and I'm changing the pressure, you see that if I increase the pressure at a fixed temperature, the enthalpy is going to go down, and then when I reach the bubble point pressure, then after that it's changing trend and it's going to go up. And the same thing for different temperatures, and if I increase the temperature, the enthalpy is going to increase also, so it's going to go up. In this case, as I increase the temperature, then the bubble point is also increasing. So then this change of trend, this point at which the curve change of trend is moving to the right. Now for the gas, for the same conditions, in the saturation, I have gas. So then I will have this trend, which is like a concave curve. Okay, and if I increase the temperature, again, the enthalpy is going to go up. And then at some point, I reach the bubble point, and then there is no more gas. So it doesn't exist anymore, the gas phase. Now on the right you have if the fluid is a gas, and you see here the same thing for different temperatures and the change of pressure, what happens with the specific enthalpy of oil, and you see that it has again like a downward trend, but now it's a bit non-linear, has some non-linearity, and then after that this stops to exist. In this case, if I increase the temperature, then the dew point is going to be smaller and smaller. Okay, so that's why now the curve stops earlier at higher temperature. Okay, but that's because that's how it is in this example. The gas has a bit of this trend going up. Okay, but now it looks like an RS type, a small RS, and then it changes trend, and then it's going down after the dew point. Okay, so that's how it looks like. So going back to our segment of tubing to know a bit how do we do our calculations. So we have our segment of tubing that we have discretized in different parts. Has to be small enough. 1, 2, and then we have some Q here. Okay, and then we can say that Q is equal to the mass flow times H2 minus H1 plus delta Z times G, okay, which is the Z2 minus Z1, which is going to be this difference in height. And typically we start from a point from which we have the conditions are known. So let's say pressure distribution is known. Typically, I have to solve both pressure and temperature at the same time, but for this case, let's assume that the pressure distribution is known. Okay, that means that I have P for all the sets in the tubing. Okay, and let's see that I start from PWF and TWF, which TWF is equal to TR. Okay, so I have P and T. That means that I have the H1, this is known, okay, because the H1, remember, it contains of X gas 1, X oil 1, and X water 1. All of these I will have if the pressure and temperature is defined, and then I need the H of gas 1, the H of oil 1, and the H of water 1. And all of this I can find from the table. Simply I have P and T and can interpolate from the table. Okay, so H1 is known. This one is known. Mass flow is also known if I have to know how much fluid is circulating through the tubing. And then this Q I can express in terms of, and we will see that soon, but we can express that in terms of, could be a function in terms of the temperature of the fluid, okay, the temperature 1 that I have, and the temperature of the formation, okay, because it's the two extremes in temperature. This is temperature of 1. Okay, I can express it, let's say, in terms of that temperature. Okay, although it won't be, if I have a finite section of tubing, it will be maybe more fair to take some average temperature. So T1 plus T2 divided by 2, for example. Okay, but I can now do an explicit upstream discretization and say that the heat is simply this temperature minus the formation temperature. Okay, this is going to be expressed in terms of that. So let's say that I can approximate that guy. Okay, and then I clear out the H2. So H2 is going to be Q divided by mass flow plus H1 minus delta Z times G. So in this equation, if we have the conditions at the inlet of the section, we have the mass flow, we have the heat rate, and then we have the difference in elevation, then we are able to find H2. Now to find the temperature, we have P2, we assume a value of T2, and then we calculate H2 calculated. And then we compare this value calculated with the value that we obtained from this equation, and if they match, that means that the temperature that we assume is correct. If they don't match, that means that I have to iterate on the temperature until I find that these two are the same. So finding enthalpy, it's an iterative process. An approach that is used to avoid this iteration is to express the delta H as a function of the specific heat at constant pressure times delta T. And this works fairly okay for liquids, but for gases, then the Cp is a strong function of pressure and temperature and require frequent update. So by doing that, the delta P in terms of the temperature, the delta H in terms of the temperature, then I can substitute on that equation and I can now don't require this iteration, but I can just clear out the temperature. But it's not, it might not be very accurate. So let's go now to the heat transfer term, the Q dot. And the Q dot term is typically expressed like that. So we have an area, which is the length times the perimeter of the pipe, 2 pi r. This I is a reference radius. Could be, for example, the inner radius of the tubing that is often used, but can be, in theory, it could be any radius that I want. Then we have the delta temperature, which is the formation minus the ambient. And here the sign is made such that it's consistent with the sign convention for the energy equation shown above. Q is positive when entering the tubing, the fluid, and Q is negative when leaving the fluid. Okay, so in this case, if the fluid is hotter than the formation, then we have cooling, which is negative, that makes sense, and opposite if it's the temperature of the fluid is lower than the temperature of the formation. Then we have this U, which is the overall heat transfer coefficient, and that's what represents all the, in a way, all the layers that you have in between the fluid and the ambient, all the different layers that you have. And this U, we have to be careful. This U should be expressed in terms of this same radius, because if I use the inner tubing radius, or if I use the production casing radius, this U will change slightly. The units of U, it's here I have heat, which is in terms of watt. I then divide by an area, which is meters squared, and then I divide by a delta T, which can be Kelvin or Celsius, because it's a differential, will give the same. And then this is the units of U, watt over square meter times Kelvin. We typically don't work with Q in watt, but we work with Q per unit of length, and that is, or in differential terms, the QDL. And that is what our energy equation was based on, we expressed it on this differential equation, dQdl. But it's going to be simply, if we remove that, it's going to be simply 2 pi r times U. Okay, so now let's see how do we find that U, and how do we kind of account for what's happened between the fluid and the ambient. Okay, we have different heat transfer mechanisms. So let's talk first about conduction. Conduction is what occurs in solids. The molecules and the atoms don't have much space to move, and they simply vibrate next to each other. And those that have higher temperature, they vibrate more, and then the vibration is spread out through the material to regions where the temperature is lower. We have two conditions: steady state. This dQdl I can express in terms of 2 pi k is the thermal conductivity of the material. For metals, this is quite high. For cement and others, this is quite low. Then we have the difference of temperature between the two walls, the radius, one at one radius and one at the other radius, and the ratio between the outer ratio and the inner radius. We also have transient conduction, and that occurs typically in the formation. When I start up the well, for example, then maybe if the fluid is hotter than the formation, it will take some time for the formation to get hot, and that has some effect on the U. But we're going to talk about that case a bit later. And then we have two other heat transfer mechanisms that we should, or one heat transfer mechanism, we should be careful. So we have forced convection, in which we have a fluid which is flowing over a surface and then it's exchanging heat. The bulk of the fluid is at a given temperature, the wall is at another temperature, and we have a heat transfer. And we have also free convection, in which we have a stagnant fluid between two walls, but then these two walls, they have different temperature, and due to the difference in temperature, they cause a difference in density, and they have caused some natural circulation. So that's what's called free or natural convection. The good thing is that these two mechanisms, they can be expressed with the same equation, which is similar to the equation we presented here, the perimeter, the difference in temperature, and then we have the H, which is convection coefficient, heat transfer coefficient. And this will be different if I have force or if I have natural or free convection. This coefficient I typically find from a dimensionless number called the Nusselt number, which makes the ratio between the convective heat transfer and the conductive heat transfer. In convection, we also have some conduction. The only thing is that the convection part is more efficient because we usually have more movement, and then the molecules, they can exchange heat in a different way. And if I have that, then you see it's a ratio between the H and this thermal conductivity. Okay, and if I have that Nusselt number, then I can clear out the H if I have the representative length. And if I have forced convection, the Nusselt number is typically expressed in terms of a Reynolds number and Prandtl. And if I have free convection, that Nusselt number is expressed in terms, maybe a correlation in terms of the Grashof number and the Prandtl number. But keep in mind, so here in this, for example, to calculate this Reynolds, I need velocities, I need densities, I need viscosities, so I need some fluid properties. And for doing that, I typically need the temperature first. And also the velocities. I have to know how much I have of each phase, and that comes from the temperature. So sometimes it can be a bit of an implicit process because I need this to calculate the H, then I need this H to calculate the U, and then I need the U to calculate the temperature. And then after I have the temperature, well, I have to verify if that it was a good assumption. So it could be that the process is a bit implicit. Okay. I want to call to your attention that be careful. So we have used H for different things in these lectures. So H can be pump head, which is the delta P divided by the density times the gravitational acceleration. H can be specific enthalpy, so H U plus P times V. Or H can be force and free convection coefficient, this that we shown here. So be careful, and depending where you see it used in which equation is used, so you can find out very easily, what H are they talking about. Okay, but be careful, it's a bit unfortunate. We use the same letter for these three variables. So let's go to an example to see how do we calculate that U. So we have this configuration, generic configuration. We have fluid flowing through the tubing. We have some temperature of the bulk of the fluid, and then we have some temperature at the wall. Then we will have some heat transfer. If this is hotter than the temperature, inner temperature of the tubing, we have heat transfer outwards. We have that is losing heat. And that what happens here is we have forced convection. Then we have conduction in the tubing wall. Then we have these two walls of the annulus fluid. The completion fluid can be mud, for example. These two walls are at different temperatures, and then that causes some circulation of fluid in the annulus, going up and down, and that is free convection. And then we have conduction in the production casing wall. Then we have conduction in the cement. Then we have conduction intermediate casing, and then we have conduction in the cement. And we're going to stop there. We're not going to take the formation yet because we know the formation is some sort of a transient process. Okay, but we're going to say simply the temperature at the formation wall is TWB. Okay, then to find out the heat transfer coefficient, we know that the Q across all of these walls is the same because we should have conservation of heat. Heat is not that it's being lost any place or being accumulated at any place. We're talking about like a steady state process. So the Q should be the same for all of these layers. Okay, and typically our heat term, the Q, we express in terms of the TF minus, so the two outer temperatures. So we want to express the heat, this Q, in terms of that. We know we can express this Q in terms of each mechanism that we have. So for example, on each delta T. Okay, this Q will be in terms of the force convection coefficient times the delta temperature here. So what I'm going to do, we're going to do a trick. We're going to have expressing all these temperature differentials as the Q and the mechanism that is happening in each one of these layers. I'm going to add all of them up. And when we add all of them up, T minus TTI and TTI minus TTO, they are going to cancel out. You'll see something like that. So this is in the force convection in the tubing, conduction in the tubing. This is conduction in the free convection in the annulus. This is conduction in the production casing. This is conduction in the cement between the production casing and the intermediate casing. This is conduction in the metal in the intermediate casing, and then we have conduction in the cement. So when you put all of these one next to the other, they cancel out. Okay, and you end up with what you want, the two extreme temperatures. And then this is going to be equal to the heat, which is going to be common for all of them, divided by, depending on the type of mechanism you have. Okay? So then if you take out as a common factor dQ/dL, you almost have what you need. Remember, what we are looking for is this expression up here. Okay, we have the delta T, we have the Q, and we have a term which we have an area, and then we have the U. And that's where it comes the selection of which area to use for the heat transfer. So one area which is typically used in wells is the one defined by the inner radius of the tubing. So then I can multiply up and down, not to modify the expression, the inner radius of the tubing. And here you see that when I multiply all of this, this is going to disappear, cancel out, and then the 2 pi is going to cancel out in most of the terms, but the radius, the internal radius of the tubing, it will be multiplying the upper part here. Okay. So the u then, it's 1 over this expression. That's going to be my u. Neglecting, remember, we are neglecting now so far what happens in the formation. We're using simply the T at the wellbore, at the sand face. That's going to be our temperature referenced, our ambient temperature. So it's not always that all the terms here are important. Sometimes some terms might be more relevant than others. I tried to make here in this text some analysis of order of magnitude of the terms. So for example, this H, it depends on the flow, what kind of flow pattern I have. I might have flow of liquid, I might have flow of gas, I have bubble flow, I might have a slug flow. This H might change. I found some numbers in the literature. They say, well, it ranges from 100 to 50,000. And then because of that, it's going to range this, the inverse, to 1 to the minus 5 or 1 to the minus 2. Okay, so it can be very small or it can be not so small, 1 to the minus 2. The conduction in the metal that we have for the term on the tubing, production casing, and intermediate casing, this I was trying to look into some numbers, ratio between the radius, external and internal radius, and that typically can give an order of 1 to the minus 4. So it's relatively small. So this could be relatively small and this can be relatively small. But now if we look at the conduction in the cement, because the K is different, the K instead of being 45 is 0.3 to 2, then this number, this conduction in the cement is 1 to the minus 2. So it's actually 2 orders of magnitude bigger than this term. And then the free convection in the annulus, this term that I have here also depends because the H is small, can be 100, is in the lower end of the force convection coefficient, and then this also can be quite big compared to the rest. So my message is that it's not, some terms are more important than other terms, and in this case the conduction in the cement and the free convection are actually dominant compared to the rest usually. Okay, because they are several 2 orders of magnitude bigger than the rest. Then let's talk about heat transfer in the formation or the soil. So there we have is a transient process, and we can use this equation, which is this energy equation, but applied for the solid and in the radial geometry. So we have the temperature of the soil, we have different radial positions, and we have also the time change. We have the density of the formation, thermal conductivity of the formation, and the heat capacity of the soil. And that equation we typically want to solve with the condition that at initial time for all positions, then the temperature is the initial temperature. Far away at a high radius, far away from the well, we're going to have that there is no heat transfer anymore. So the differential term, this derivative of TE with dr is 0. And then we also have the condition that exactly at the boundary, the heat transfer should be equal to whatever is coming from all the other layers. This is the term that we have calculated before. And that's how we're going to have our connection. But this is a transient equation that we need to solve, and we should solve it numerically. But there are some researchers that they have found an approximate and analytical solution that we can use. So one good noteworthy work of that time of doing that work was the work by Henry Ramey. A wellbore heat transmission is called the paper, and was proposing a solution to this equation, an approximate analytical solution to that equation that can be used to calculate a new U. Okay, but I'm taking another solution from these two researchers, Hassan and Kabir, that they propose something like that. So TD is dimensionless temperature, and this is temperature at the sand face, and we have the dimensionless time, TD, which this TD is the thermal diffusivity of the soil, which is simply a combination of these factors: thermal conductivity, density, and heat capacity. And then we have the time, and then we have the wellbore radius squared. So if we have the time, then we can have this dimensionless temperature. And then we can substitute the equation we have for the u dq dz in terms of the u and the delta t. And then you see that you have the temperature at the sand face in both sides, and then you can substitute this expression there. The details are in my compendium. We're not going to go through them here, but what ends up is that you can find the equivalent or an effective overall heat transfer coefficient, that is your original coefficient, neglecting the formation, times the thermal conductivity of the formation divided by the thermal conductivity of the formation plus the dimensionless time coming from this expression, the radius of the tubing, and the u. Remember this u, it was made in terms of, that reference radius. And you see here the effect it has, the t, is that if it's zeroed initial time, so you have little effect of that td, okay, actually will be 0. Okay, so it simply tells you that is u, is the initial u. But when the t time starts to increase, then this td is also getting bigger, and then all of this term is getting smaller. So what you get effectively is you get some insulating effect due to the fact that the formation is getting heat up. Okay, the formation is increasing its temperature, and then this is getting smaller and smaller.